Greetings, my young mathematician friends. We are going to be looking today at two things that are related, but not necessarily always related. So we're going to be discussing something called a power series, as well as something called an interval of convergence. You will see this spring when we return to the topics of series one more time, that interval of convergence is not only about power series, it's about other things as well. But these two topics are kind of nice. They're good. All right, so these first three questions are warm-up questions. We're coming up on a quiz, and so I wanted you to have a minute to think back on the things that you learned from Mr. Covey the other day, and that's what these three questions are. So please pause, try the three warm-up questions, and then come back. Okay, so the question that we have for these three problems, talking about series convergence or divergence, this is totally one of the themes in this class. It's kind of a big deal. And we're kind of doing the light version of it right now. Maybe that's depressing for me to say. If you're having a hard time, I'm sorry about that. Please come to PLT and get more help. But right now we are doing the version where there's only really three possible things that you could even try. There are only, it's like when you're a little kid and like one of your parents decides to give you like a toolbox and you have a screwdriver, a wrench, and a hammer. That's it. You don't have the socket set. You don't have a drill. I mean, you're a child, okay? So you have three things that you can try, and that's legit it, okay? You have your nth term test, which only works to say divergent. So if you find yourself saying, this is convergent by the nth term test, what actually kind of gives me heart palpitations to put those things together. Those things don't go together, right? No, just no. It's the nth term test that only can tell you divergent. That's all it does, okay? So it's not like an either or situation. Is it this? And if the answer is, yeah, I've got something that isn't equal to 0, then I know divergent. If I have something that equals 0, I don't know anything. Okay, geometric is one of my three tools, and partial fractions. So the tool of partial fraction decomposition, which shows me that I have a telescoping series. Oh, my stylus is lagging. It's very hard to write neatly. I mean, I have crap handwriting anyway, but anyway. Okay, so those are the three options, and you can see here how I did the questions. Now, the first one you actually could do as I show it. You could have done it as well with nth term test, but I think geometric is nice and clean. So that's geometric. It has the wrong kind of ratio, therefore divergent. 2 and 3, I did both of these with nth term test. Only thing nth term test can justify is divergent, and the second one was divergent because the limit was 2/3. 2/3 and 0 are not the same number. Number 3 is divergent because the limit there does not exist. Something that does not exist and 0, not the same thing. 0 actually exists. So if you're saying does not exist and you're saying 0, you're saying different things. Okay? So those two not being the same, that tells me nth term test. Try to avoid thinking, and certainly saying, nth term test applies or nth term test doesn't apply. That's not really like the right lingo, right? It's either this limit is non-zero, therefore diverges by nth term test. That is what you can say. All right, other things, other versions of that, don't say those. All right, power series. Okay, so for our purposes, we can think of a power series as being an infinite polynomial. God, that's great. I love polynomials. So having one that goes on forever, that's just delightful. So remember that a polynomial is when you have integer powers of a variable. So our variable here is x, and we have integer powers of that x. And then notice here we also have these different like a sub 0, a sub 1, a sub 2. Those are just different like multipliers. Okay, they are not the variables. They are just numerical constants, multipliers, if you will, that could be on each term, like a polynomial has, right? Like let me think of a polynomial I like. Let me see. I like the polynomial function this. That's a polynomial. These little like coefficients, that's what these like guys are, okay? Fine. So the idea is an infinite polynomial, and you can slide that polynomial so it would move to the left or to the right, and have it be centered, we would say, somewhere other than 0. So you might have like x minus 4 or x minus 6 or x plus 1 in parens with each of the different powers. That still is a power series. Okay, don't obsess about that. We're going to, like, you'll get the feel of it through the problems, not necessarily through the definition. Okay, so this example says, what is the sum of this power series and when does it converge? Now, you might be like, how am I supposed to do this? Okay, well, just kind of stay calm. Your pencil can help you figure things out. I can see in this that from one term to the next, I am multiplying by x. Every single time, multiply by another x, multiply by another x. What does that remind you of? Hope it reminds you of a geometric series. Right? A geometric series is where you have a constant multiplier, and here we have a multiplier of x. Right? Every single time, it's multiplying by x. And I know that geometric series, if they converge to the first term, which in this case is the 1, over 1 minus the constant ratio, which in this case is x. So what I was using in my brain there was this idea. Oh, sometimes I get ahead of myself. If the absolute value of r is less than 1. Okay, so this is a fact that we know about infinite geometric series. And so I'm using that formula, and that is only going to be true if my ratio, which is x, is less than 1. An alternative way of saying this part is to say that x has to be between -1 and 1. Guess what? That's my interval of convergence. So this infinitely long polynomial power series is equivalent to just this little short statement if x is anywhere between -1 and 1. So if I were to go back here and substitute in like a half, look, what is up? I would say I was having like some kind of caffeine thing, but Diet 7-Up, no caffeine, crisp and clean. I don't know what's going on. Okay, so if I were to plug in a half for x, blah, 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 that's going to be equal to this. That's a true statement. If I pick something outside of this, I will get a result that is not equal to this. Okay, so this is my interval of convergence. You think of it sort of like the domain that makes this entire statement true. Probably I should write more on this slide, right? That probably makes it more clear. Oh my gosh, seriously, Lemke. Okay, here's 4 and 5. So this question says, find the sum and the interval of convergence for each power series. Okay, that sounds pretty good. In number 4, what's our ratio? It's geometric in structure. So my constant ratio is x over 3. Right? If you weren't sure about that, you could write out a few terms. Plug in 1, plug in 2, plug in 3, plug in 4, right? Until you see it. And I know that a geometric series is convergent if the absolute value of its ratio is less than 1. That is equivalent to saying my x over 3 has to be between -1 and 1. If I multiply through by 3, I get that. So my interval of convergence the values for which this series would add up to a specific thing is between -3 and 3. Now part 2, oh actually part 1, I wrote it kind of backwards. The first part said to actually find the sum. So actually finding the sum, I'm going to remember this is acting like a geometric, and so I'm going to take the first term over 1 minus r. And if I substitute in my sum, let's see, we already said the ratio is x over 3. And this index starts at 1, so if I plug in 1, my first term is also x over 3. Just to tidy that up, I just find that a little, don't you find that a little awkward? We could just multiply through by 3 over 3, for instance. Okay, that's just a 1 in blue. So x over 3 times 3 is just x. Distribute this 3. I've got x over 3 minus x as my sum. So the two parts, find the sum. Here it is with an awkward looking 3 and the interval of convergence right here. Ta-da. I'd like you to try number 5 by yourself. Come back in a few. Okie dokie. So the purple writing is where I began. I said my constant ratio is x minus 2. That's what I'm multiplying by over and over again. I sandwich that in between -1 and 1. I solve the inequality, which means isolate the x. I did not say in the previous question that you could definitely use inequality notation, but fancy pants calculus people love to use interval notation because guess what? It's an interval, so interval notation, very appropriate. Not wrong if you said x is between -1 and 1 using inequalities, that's okay. All right. Then if our x value actually meets that condition, if x is from the interval of convergence. So do you know this notation? That just means is an element of, okay? So if x belongs to this interval, if x is somewhere inside of that interval, okay, is an element of, then my sum is going to be my first term over 1 minus r. Clean that up a little, and you get the expression I have there in black, the x minus 2 over 3 minus x. All right. The rest of it, it's just practice, my friend. You totally have got this. So you're going to work these 4 problems to the best of your ability. Then you're going to come back and super quick check with me. That's all we've got today. How about it? Okay, so time to pause and come back and check. All right, so I hope you had fun doing those 4 problems. Question number 6 is one we want to do with partial fraction decomposition. I have a feeling that's going to work out great. The signal for that is that the denominator factors. So I have a 1 in the top, that's fine. I could have a different number, like I could have 7 up there. I could have something with an n up there possibly, but if I have something that factors in the bottom, that is like your ding, 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 time to see if it telescopes. So in purple, that's where my writing went first. I actually went, I wrote this, I did the factored, I had to factor the bottom. Then I went into the purple writing. So the purple writing is where I'm going to say, well, let's say that this fraction that I have splits up like this. Then you multiply through by the denominator, like the fancy long denominator, n plus 3, and you get this line. Now a caution. You guys, I've been through this class a few times now. I'm getting pretty good at it. Maybe one of these days I'll pass. But right here is where a lot of people start writing. They decide, oh, I don't want to save time. I'm not going to write this. Okay, you see the thing that happens though, I'm just saying after grading hundreds of calculus papers, is people will get to here very successfully. They'll find A and B, and then they'll put the A part with the wrong denominator, and they'll put the B part with the wrong denominator because they didn't take the time to write this. So please take the time to write it. If you start out with the green highlighted line, you might mess up, and then everything goes bad off of that. It's really unfortunate. Okay, so once you have A and B, then you go back to the thing I circled. Okay, go back, plug in your A, plug in your B, and you get this. And then because I hate arithmetic, I try to minimize my arithmetic. That's my personal choice. You did not have to do what I did, but I factored out the 1/3 because I just want less arithmetic. Then you plug in 1, you plug in 2, you plug in 3, you plug in all the things until you start to see which things will remain and which things are going to drop out. When you're confident you have found that, you can be done writing. Until you see, you have to write enough that you're going to see. Like sometimes people are like, how do I know that the 1/7 is going to cancel out later on? If you don't see it yet, keep writing more terms and you'll see the pattern. You're like, oh, I have a positive of this and I have a negative of that. Those are going to cancel, right? And then the things that remain, that's what this answer is, okay? Question 7, a little bit more straightforward, I hope. Geometric, ratio of -4/5. That meets our condition of the absolute value being less than 1. And then use your sum formula that we were just using earlier in this class, or earlier in this video, and you get 5/9. All right, 8. It's fantastic. Nth term test. Okay, now remember, only 3 tools in the tool belt right now. It's not telescoping, because are you going to factor that bottom? No, you're not. And it's not geometric. It's not. Like, look at it. Write out a few terms. It doesn't, like, have a constant multiplier. So it must be the 3rd tool. The 3rd tool is nth term test. And so then you take the limit of that sequence, think of n going to infinity. Those values are going to get closer and closer to 2/5. You might remember some stuff from math analysis around that. And if we say the limit is 2/5, guess what? 2/5, very important, that 2/5 is not 0. And so if I have a limit that isn't 0, that means that the series diverges. The sequence converged. It had a limit of 2/5, but the series diverges. Number 9 is on this page because of a final exam question from the first year I taught BC. I asked a question kind of like this, thought it was really nice. And there were students who were confused by the fact that there was a 6 instead of a 1 in the numerator. And I went back in my notes at that point and realized, rats, 16 or 18 weeks ago, I never had a problem that didn't have a 1. That's not good. So here we are. We won't make that mistake again. Fine. We do our partial fraction decomposition. You get your constants of 3 and -3. You do exactly the same kind of thing we were discussing in number 6. And you get your answer, okay, 11/3. Have a powerful day. Converge on some more mathematics. Whoa, those are bad. Have a good day.